Thank you, Professor Rajesh Gopakumar. Yeah, and it's a great pleasure that we could actually organize this. Actually, it was planned to be, as you mentioned, as a like a one-on-one or like a offline meeting. But unfortunately, given the circumstances, we couldn't do it. So, but this is good. So, thank you very much for the opportunity. Okay, all right. So thanks. So before I start, I would like to thank ICTS, Professor Rajesh Gopakumar, the team that vets the proposals, and Ms. Aruna Mahinderkar, and then Divya Ramesh for for making it so easy. The thing is, we just need to submit the proposal, and then after that, they actually take care of a lot of different things. So thank you very much. And before I start, actually, I'm going to give the lecture, this lecture and the next lecture. I'm sorry if you were expecting Professor Pedro Caro. So he actually had a bereavement, and so he actually informed, that so given his state of mind, he is not able to join. So, I'll actually be doing in his place. So hopefully I will do justice to what he was planning to do. So let's see. Okay, so I'm actually going to share my screen. Okay. So I suppose you can see my screen, yeah? Anyone? You all can see my screen?
Yes, we can see your screen, sir.
Okay, thank you. So, yes?
That's okay.
Okay, all right, thanks. And so the topic that I'm actually going to do, which was what Professor Pedro Caro was planning to do, is an introduction to the Calderon inverse problem. And Tuhin Ghosh, who will actually be lecturing on giving 2 lectures later this this evening for us over here, will be on the fractional Calderon inverse problem. So I'll actually be doing the Calderon inverse problem, which Calderon originally started. Okay, so so what I want to do first is to give the conductivity equation, and I'll actually explain what the Calderon inverse problem is. So the conductivity equation, and this is so basically this follows from the Ohm's law. So we have, let's say, let U be the electric potential in a medium omega. Okay, and let's say it's a conducting medium, and let I be the current, I of x. This is U of x. Be the current. Okay, so now the electric field E can be written as minus grad U, and the Ohm's law, which is that the current is directly proportional. So current is directly proportional to the electric field. So we have E of x. So this is equal to R of x times I of x, where R is the resistivity of the medium. Okay, and so if I assume, so if I call conductivity, so conductivity as the inverse of resistivity, so I'll call gamma of x. So I'm assuming that, so I will put some assumptions on this gamma of x. which is that it's L infinity and it's bounded above and below by positive constants. So 1 by R of x. Okay. Now, assuming that there is no sources or sinks. Okay. So let conductivity be denoted by this. So assuming no sources or sinks. So what it means is that the current flux. So the current flux through any medium, let's say ball, B is 0. Okay, so what it means is that if you consider, let's say, a ball, and then if you consider, so this is what it means for nu I, so ds of x, so this is equal to 0. And if you use the divergence theorem, so using the divergence theorem, right? So this tells you that so this here, so this quantity here is the same as integral over b of and now if you just put it all together, right? Because we have I of x is equal to E of x by R of x, which is the same as gamma of x. So this is the same as integral over b of gamma of x, and then you have E of x dx is equal to 0, but this is the same as integral over b. Okay, you can put with a minus sign if you want. But this is true for all such balls. So this implies, so this implies that we have so this is what is called as the conductivity equation. So the conductivity equation. Okay, so then so before I state what the Calderon problem is, so let's consider the following Dirichlet problem. So Dirichlet problem. So and then u on the boundary, let's say I specify this Dirichlet value f, right? And we'll not worry about what what space this f is and things like that. But we consider the Dirichlet problem, and assuming that this gamma here, so gamma is in between these two, in which 1 by m, so gamma is an L infinity and it's also bounded below by a positive constant. So then by the standard, by your the course in PDEs, you may know that this problem here, this is well posed. Okay, so now so then this is this, let me call this is star, and star is well posed. So by the way, I usually don't watch the chat while lecturing. So if you have any questions or anything is not clear or anything like that, please do interrupt. Please feel free to interrupt at any point of time. Okay. I don't know if somebody else is watching the active chat, but I normally don't. Okay. So actually, just in case, let me just put the chat over here. Okay. All right. So star is well posed. Okay, so now what is Calderon? What is Calderon? So what is the problem that Calderon asked? So Calderon asked the following problem. And so what he wants to, so what the problem that he asked is the following. So the question is to determine the conductivity of the medium, so the conductivity gamma from Dirichlet and Nyman measurements on the boundary. So what do I mean by that? Now you specify a Dirichlet value, right, which is your f over here. Okay, so suppose you specify this Dirichlet f, and then you measure the outgoing current flux, which is given by du d nu. So okay, so this is on the boundary, and this is also on the boundary. Okay, so this is the so nu here. Oh, I forgot to mention, nu is the unit outward normal, and u is the unique solution to star. Okay, so the problem that Calderon asked is, suppose I specify a Dirichlet value, and then I measure the outgoing current flux, and now I can do this, you know, for as many measurements that I want. And the question is, from this boundary data, so let me call this as n gamma. So from n gamma, is it possible to determine gamma of the medium? Okay, so is it possible to determine determine the conductivity gamma of the medium? So this is the original problem that Calderon asked, and Calderon was actually motivated by, oil prospection. So he was actually working as an engineer in his native Argentina, and so he was motivated by using this question in oil prospection, that is for determination of determining oil in the subsurface based on boundary measurements. And nowadays, this is actually I don't know if this is actually used for oil prospection, but this has found its use in a lot of other applications. One of them being mammography, lung cancer detection, and several others. And it was also found as a potential, thing in cloaking. Okay, so I'm not going to talk about all these things. What I'm actually going to talk about is the original approach that Calderon had, and what was the how this problem was actually solved in 3 dimensions and higher. Actually, I'll also give a brief history of the problem and some open questions as well. Okay, so some brief history. So Calderon, so I will just put C here. So Calderon addressed uniqueness question for a linearized problem. So I'll actually do this linearized problem. And for C2 conductivities, so for C2 conductivities and in dimensions n bigger than or equal to 3, this problem was settled by Sylvester and Ullmann in their famous Annals of Math paper, I believe 1987. Okay, so this and we will also see this. We will see their construction, the construction of Sylvester and Ullmann. But I'm not going to give the construction as it was done by them. We will actually use a more versatile method, which will actually apply to other situations as well, based on what is called as Carlman estimates. So this, so in dimensions n bigger than or equal to 3, and we will also see where n bigger than or equal to 3 plays a crucial role. And so in 2D, so this problem was done. This problem was done by Nachman, and Actually, I should also mention Astella Pivarinta and many others and others. So 2D problem is actually much harder, significantly harder compared to the 3D and 3 dimensions and higher. I'll actually give a motivation as to why the 3D is easier, or 3 dimensions and higher is easier compared to the 2D case. And so now the thing is, so this is as far as what is called as C. So these are all what are called as the full data Calderon inverse. So what do I mean by full data? So what I mean by full data is that there is no restriction on my F, where actually the support of F lies, and there is also not restriction on where I can measure, that the conductivity where I can measure. Okay, so now I would like to give some history about partial data Calderon inverse problems. So no restriction on Dirichlet data. That is, my F is allowed to be supported anywhere on the boundary, right? There is no restriction on the support. Okay, and Nyman data. So Nyman data. So which is the gamma du du, the outgoing current flux. Okay, so this is measured only on slightly more than half of the boundary. Okay, so this was done by Buchheim and Ullmann. I believe in early 2000. I don't quite remember the year. So Buchheim and Ullmann in 2000. This was the first time they actually used, or to the best of my knowledge, that they actually used Carleman estimates in solving elliptic inverse problems. Elliptic, in this case, this is Calderon would fall into the class of elliptic inverse problems. Buchheim and Klebanov in earlier, they have actually used this, the method of Carleman estimates, formally determined hyperbolic inverse problems for settling uniqueness question in formally determined hyperbolic inverse problems. So this will be done by Professor. Okay, so I don't exactly know what Professor Rakesh is planning to do, but one of the things would be this. Okay, and so this is no restriction on Dirichlet, and then and Nyman data is measured only on slightly more than half. This was done by Buchheim and Ullmann, and the case in which if you have Dirichlet and actually sorry, I just take back one thing. So okay, so this is exactly not what they do. So there is actually restriction on the support. So some restriction. So there's some restriction on Dirichlet data, and Nyman data is measured on slightly more than half. So roughly speaking, what this so let's say this is the medium, and let's say you have, so you make Dirichlet measurements, so that the Dirichlet data is supported on this piece, and let's say the Nyman data is only measured on this piece. So with this, Buchheim and Ullmann actually solve the inverse. Now, the case in which Dirichlet and Nyman are measured on possibly small subsets, are measured on possibly small subsets, was done by Koenig, Sjöstrand, and Ullmann. And again, so this was, I think, 2005 annals paper. So again, I just want to emphasize that this here, the dimension is bigger than or equal to 3. And here again, the dimension is bigger than or equal to 3. And there have been, for instance, I would like to mention that the work of Astella and Pivarenta. So this actually fully, in effect, fully solves the Calderon, the full data Calderon inverse problem with only L infinity conductivities in the 2D case. But unfortunately, in the high dimension, that is 3 dimensions and higher, how much low regularity that you can go is still an open question. Okay, so these are some of the developments in the case of the Calderon inverse problem. So let me, by no means this is a comprehensive history. So this is, I just want to make a mention. So this is not a comprehensive history. This is more in line with my interests and the one that I am most familiar with. So there have been other, as I mentioned, other developments as far as low regularity is concerned, as far as how partial Dirichlet, how partial Nyman that you can actually measure. So I would like to mention just one before I actually get into some definitive calculations. So the one that is quite interesting is the following. So suppose you have a bounded domain omega, and you take a small and open subset of the boundary. Okay, so this is here. Now your Dirichlet and Nyman are measured. So okay, Dirichlet is supported and Nyman is measured only on this piece. Only on this piece of the boundary. Then the question is, from this information, so from this information is conductivity gamma uniquely determined. Now, actually in 3 dimensions and higher, so even though 3-dimensional cases are easier, so surprisingly in dimensions n bigger than or equal to 3, this problem is still open. Okay, and in dimensions n is equal to 2 and n is equal to 1, the Calderon inverse problem, there is not enough, you cannot actually determine the conductivity in on a wire based on boundary measurement. So n is equal to 1 is not interesting, and n is equal to 2, this problem has been solved. And so some names that have contributed significantly here is, it's a very there's a very nice paper of Buchheim, and then there is Ullman, Leo Zhu, and Guillermo. Then there is actually Yamamoto, and there is one more person that whose name I'm forgetting. He's from Colorado State University. Anyway, if the name comes to me, I don't want to leave out that name because it's a big name. So in the sense that that person has contributed significantly. So anyway, so in 2 dimensions, this is actually solved. In 3 dimensions and higher, this is actually open. It's very surprising. So if you're able to settle this one can become instantly famous in this community. Okay, so now the question is, so why 3 dimensions and higher easier to solve? So if you think of it, so in 2 dimensions, so if you just think of just as a formally dimension counting problem, right? So what you have is your you have this map n gamma, which takes gamma to gamma du d nu, right? Now this gamma here depends on, so this is, sorry, I made a mistake, so this should be f going to gamma du d nu. Now this is a function in n minus 1 dimensions, right? Because it's only a function on the boundary, and this is also n minus 1 dimensions. So the so-called data that you have, that is this boundary operator n gamma, which is the boundary operator, right? It's the, if you want to think of it as the Schwartz kernel of this the boundary operator, right, which takes f going to gamma du d nu. So this depends on 2n minus 2 dimensions.
Hello, Venki. Can I ask a quick question?
Yes.
So I just want to double check that, is there a restriction on the smallness of the boundary for this problem n equal to 2, or it's true for any arbitrary small enough part of the boundary if you know the data?
Any arbitrary small open subset of the boundary is enough. That is, you're referring to this problem, right?
Yes.
Yeah, any arbitrary small subset of the boundary is enough.
Oh, okay.
Yeah.
Okay, thanks.
And one would actually like to solve this in the for arbitrary small subsets in which both Dirichlet and Neumann are measured on the same open subset. That is what one would like to solve in 3 dimensions and higher, but it is you know, nobody knows how to do it.
Yeah, but for n equal to 2, it's settled, right?
N is equal to 2, it is settled.
Okay.
That's because the method of construction. So I will come to this, what is called as this. Okay, I'm sure you know this, but the method of construction of complex geometric optics. So you can actually use this method of stationary phase to construct a lot more solutions in 2D, which you are not able to do this in three dimensions and higher. So that seems to be the difficulty in 3 dimensions and higher.
I see. Okay. Thanks.
Okay. Yeah. So n gamma, the boundary operator, which depends on 2n minus 2 dimensions. So if n is bigger than or equal to 3, right? So then we have a lot more freedom. Or in other words, a lot more data, right? Because this is just, you know, it's a very vague way of thinking about this problem. That if n is bigger than or equal to 3, you are interested in determining a function which depends only on n variables, right? And the so-called boundary operator that depends on 2n minus 2. You know, it depends on 2n minus 2 dimensions. If you think of the Schwartz kernel, it's a function that depends on 2n minus 2 dimensions. So when n is bigger than or equal to 3, you have a lot more data, right? So which means that you can actually exploit this freedom to actually solve in 3 dimensions and higher, which is actually what Sylvester and Ullmann did. But you see that if n is equal to 2, then this problem becomes formally determined. Formally determined, right? And that's where the difficulty is. And so if you look at the paper of Nachman, it's 1980 or 1990, it's an annals paper. So, you know, the construction is actually different from the construction in 3 dimensions and higher. Okay, all right. So now, what I want to do is the following. So first of all, so this is the, I want to introduce the original approach. So this is so much for history. Okay, so for the brief history. So the original approach of Calderon. And this is what actually motivated the the construction of complex geometric optic solutions. So, so roughly this is the original idea of Calderon. And so what he did is the following. So he wanted to construct solutions, and I will explain why this is why he wanted to do this. So he wanted to construct special solutions, special harmonic functions in the whole of Rn. So in Rn. So some special solutions. So what is a special solution that he considered? So this was motivated by, so the motivation for constructing these special solutions. So the motivation was to recover, was to get to the Fourier transform. So this is the main motivation. Okay, so what is the special solutions that Calderon considered for Laplace u is equal to 0 in Rn? Okay, so let's take u of x. So this is equal to e to the x dot zeta, where now zeta is a complex vector. Complex vector. Okay, now not all zeta being a complex vector is going to be a solution to Laplace u is equal to 0. But let's check. So suppose so zeta is fixed. Okay, so zeta is a fixed complex vector. So suppose suppose this u has to be a solution to Laplace u is equal to 0. So then, okay, so let's do this computation. So if you have du dxj, that's going to be zeta j e to the x dot zeta, and d square d dxj square. So this is summation, okay, not summation, zeta j e to the x dot zeta. And now Laplace u is equal to 0. So this implies that you must have zeta dot zeta of e to the x dot zeta. So this should be equal to 0. But so remember that this zeta dot zeta is not the dot product. The dot product in Cn. It's not the dot product. So what exactly is it? It is just zeta j. So for instance here, right, this is just zeta j square. So zeta j is a complex number. So okay, so zeta here is zeta 1 up to zeta n, and each zeta I belongs to C. So it's a complex, it's a complex vector in Cn. And so this zeta dot zeta that I have over here, so this is simply summation zeta j square, j is equal to 1 to n. And you must have that this is equal to 0. Of course, if you take the dot product, then zeta dot zeta is equal to 0 implies zeta itself is 0. But we are not considering the dot product. We are actually considering this zeta j square is equal to 0. So if you just expand this out, that is, if you take zeta j as, or if you take zeta as the zeta real part plus I times the zeta imaginary part, where zeta r belongs to Rn and zeta I belongs to Rn. Right now, the fact that the zeta j square is equal to 0, so this would imply, that the length of the real part should be the same as the length of the imaginary part, and the real part, now this is the dot product, a dot with the imaginary part should be equal to 0. Or in other words, what we have is that, so okay, now so what we have is that the length of the real part of the complex vectors zeta, the length should be the same as the length of the imaginary part, and these two should be perpendicular to each other. Now, if you consider, let's say in the case of 2D, right? Now, once zeta r is fixed, then there is only one, essentially one direction that zeta I can be, right? So there is a lot more constraints in 2D, because in 2D, once one direction is fixed, the perpendicular, there's only one, essentially one direction. Okay, so in 2D, so once zeta r is fixed, so then zeta I is constrained to be in the orthogonal direction, and there is only essentially one. Essentially one direction. Now, what was the motivation for Calderon to actually consider such special solutions? Okay, so this is u of x is equal to e to the x dot zeta. So what was the motivation? So the motivation was, for Calderon was the following, that he wanted to study this map, which is gamma going to n gamma. Okay, so you are interested in, so what is the original question of Calderon? Question of Calderon is to invert this map. Right, so given n gamma, I want to find gamma. That was the original question of Calderon. So he wanted to invert this map, right? But notice that, so note that this map is non-linear. This map is non-linear, right? You see, once gamma is fixed, it's a linear PDE, right? Because your PDE is actually what? But this is a linear PDE. But you see, however, this map here is non-linear. Okay, by this I mean this map is non-linear, right? Why? Because you see that if you, so once this gamma is fixed, right? Once this gamma is fixed, it's a function in omega. Once the gamma is fixed, then this is linear. But suppose you change gamma, right? Suppose you have two different gamma 1 and gamma 2, and then you suppose you put Dirichlet value f gamma 1 plus gamma 2, and the corresponding n gamma would correspond to n gamma 1 plus n gamma 2. There is no reason to expect that. It's not true either, right? So this map here, it's a highly nonlinear map. And what Calderon is asking is actually the question of inverting such a highly nonlinear map, right? So Calderon was not able to address the invertibility. So Calderon, in his original paper, it's a beautiful paper. So Calderon was not able to address invertibility of gamma going to n gamma. Okay, instead, so okay, now if in practice, what do you do? So if you are not able to study the invertibility or any properties or properties of a nonlinear map, you try to linearize the problem. Okay, so what Calderon did is to linearize this map. So Calderon studied the linearized problem, linearized near constant conductivities. Constant conductivities, which we will assume, is 1. Or in other words, what we are interested in is in the Frechet derivative. So we are interested in the Frechet derivative of the map gamma going to n gamma near gamma is equal to 1. Now, before I do this, you see that here this gamma here, so this is a function in omega, whereas this is actually a boundary operator. Boundary operator. Okay, so instead what we do is we actually want to look at something that goes from something in omega to something in omega itself, or some quantity which can be represented in terms of omega itself, in omega itself. So instead of studying gamma going to n gamma, what Calderon did is, instead of this, he focused on gamma going to q gamma. Okay, where this q gamma here, so q gamma is what is called as power, and this is simply so q gamma of f is integral over omega gamma grad u square. Actually, these two are equivalent. This n gamma and q gamma are equivalent. It just follows from integration by parts, or the divergence, or the divergence theorem, right? So instead of studying n gamma, you study q gamma. So q gamma, because this is integral, this is given as an integral over omega, whereas this n gamma is the one that goes from f to gamma du d mu. Okay, so what he actually does is the following. So he computes, so the theorem, so the Frechet derivative, of, okay, let me just write this in the following. The Frechet derivative near gamma is equal to 1 of q gamma is given by, so I'll just write this. So this is dq gamma of delta of f. So this is actually integral over omega of delta grad u squared dx. So the delta here is the perturbation, and f, okay, so if you want, so f is actually, you can think of this as the Dirichlet data. So you can think of, if you are familiar with Sobolev spaces, you can think of this as an f in h half of d omega. If you are not familiar with Sobolev spaces, no issues. You just think of a function f on the boundary, right? And okay, so there is f over here, and there is actually a u over here. So what is the relation between these two? Where u solves, Laplace u is equal to 0 in omega, and u restricted to d omega is equal to f. U restricted to d omega, that's equal to f. Okay, now why is it that the Laplacian here is come? Okay, so this you know, if you're familiar with you know, so this requires a little bit of work, right? So this here requires little bit of work, and I can give some references. For instance, one would be the original paper of Calderon. It's in the 1960s. It's a small 8-page paper. right? And the reason, okay, but what I want to do is, so instead of focusing on the calculation, so what you need to do is this: you consider gamma, you consider a perturbation gamma to be 1 plus delta, because I'm linearizing near constant conductivities. So I consider 1 plus q 1 plus delta minus q1, and then you just write this in terms of, so you want to set it up in the form of a pressure derivative, where the term, what you want to do is you want to consider a bounded linear operator, right, plus some term which is of order delta square, and as delta goes to 0, that term goes to 0, leaving you with this would be the differential derivative. So this is I don't want to focus on the calculation right now, but what I want to do is I want to see why, how one can actually get to the original solution of Calderon, which motivated later developments. But if you're interested in this computation, it's there in this original paper of Calderon from the 1960s. Okay, so so what Calderon asked, what Calderon proved. So what Calderon proved is that one can show that the linearized operator, okay, near constant conductivities is injective. So I will actually show this computation, okay, because it's actually quite beautiful. Okay, now I forgot to mention why you actually get a harmonic function. Laplace u is equal to 0, and then u on the boundary is equal to f. Okay, so the reason why we get, Laplace u is equal to 0 and u on the boundary is equal to f is because of linearization near constant conductivities. Now, if you were to linearize near other points, right? Other, let's say gamma naught, right? Which is in general a function. Let's say gamma naught is a function. Then you will actually get solutions to the conductivity equation. That is, you need to produce enough solutions. Okay, so you need to have, so you will actually come up with, if you linearize near non-constant conductivities, then your solution u with the prescribed Dirichlet would solve not the Laplace u is equal to 0, but it would be the conductivity equation. Now, producing solutions for the conductivity equation in general is going to be a very hard problem, right? And but for constant conductivities, Calderon actually produced this ingenious solution that I just described earlier, and that's what actually he does to actually show that at least the linearized problem is injective near constant conductivities. Okay, now the other thing that I want to mention is that you see that so what do I have? So the question that now one is interested in is the following. So the question boils down to, suppose you have integral over omega of delta grad u square dx is equal to 0 for all harmonic functions u. Does this imply delta is equal to 0? Because that would then show that this derivative here is injective. Just 1 second. That would show that the derivative is injective. Okay. Now, one thing that is so one thing that I want to mention here is the following: is that, so what you have grad u square, right? Now, because you're allowed to have any Dirichlet value, right? there is no restriction on what u that you can take. You can practically take any u, and then you consider the corresponding Dirichlet, and that would, with that as the Dirichlet value, you can actually approach the problem. Now, the difficulty in partial data inverse problems is that, just as an example, suppose you have the same thing, integral omega delta grad. Just 1 second, somebody is at the door. So one of the difficulties in when you consider, let's say, partial data inverse problems is that now you need to have enough harmonic functions which also now vanish on a part of, okay. So let's say you want to solve the fully nonlinear problem, then you also need to show that there are enough solutions to the conductivity equation which also vanish on that part of the boundary, right? And those are going to be significantly more difficult to construct. So that is a difficulty in partial data inverse problems. Okay, so what Calderon showed is that this answer is yes. Okay, so this delta grad u square dx is equal to 0 for all harmonic functions implies that delta is equal to 0. So now what is the construction? So the construction is as follows. So let me just do this construction, and then we will go to the nonlinear problem in the second half. Okay, so the construction is as follows. So the first step is that bipolarization identity, right? It's enough. So if we can show this for, if it is true that for all delta grad u square dx this is equal to 0, so then it's the same as this is equal to 0 for uv harmonic, right? The easiest way that one can think of, you just substitute u by u plus v, right? And for all u it is 0, so therefore delta grad u square is 0, delta grad v square, that's also 0. What remains is now just going to be delta grad u dot grad v, right? So instead of doing this, you look at this. The advantage here is that now you can work with two different harmonic functions even. So what Calderon did is the following. So he looks, let u of x be, so let's consider the following: e to the minus I x dot zeta, where zeta belongs to Cn. Okay, now for this to be a solution, as we just saw, so we must have that zeta dot zeta is equal to 0, or in other words, we must have that the real part should be the same as the length of the imaginary part, and the real part dot the imaginary part, this should be equal to 0. Okay, so now as I told you, the what Calderon did is to actually recover the Fourier transform, right? So so what we do is we just substitute a suitable u and v into this particular equation, Okay, so what is the solutions u and v that Calderon takes? So you fix a real vector C in Rn. Okay, and let us take our zeta r. Okay, now the vector C is fixed. So now you consider two complex vectors, zeta and zeta star belonging to Cn, such that zeta r, this is equal to zeta r star. So let me take this to be equal to C by T. And let us take our imaginary zeta I, this is equal to zeta I star. So let us take this to be equal to mod C by 2 omega, where omega is perpendicular to C and omega belongs to Rn. Okay, now we need to check. So what is it that we need to check? So we need to check that this zeta, and so my zeta would be zeta r plus I times zeta I, and zeta star would be zeta r star plus I times zeta I star. Okay, now what do I have? I have c by 2 plus I times mod c by 2 omega. Did I do this right? Maybe I should put one with a minus sign. Yes. Otherwise, we get the same set of vectors. Now, so now this is zeta. So zeta star. So let me take it to be c by 2 minus I mod c by 2. There you go. Okay, so I want two different vectors. Therefore, I introduce this minus sign. Okay, so initially I forgot this minus sign. So therefore, now you see that, okay, the length of the real part is the same as the length of the imaginary part. And because omega is chosen perpendicular to C, the real part dot the imaginary part, that's equal to 0. Okay, so now suppose you substitute e to the I or e to the minus I x dot zeta for u, and e to the minus I e to the minus I x dot zeta star for v. So then we would get exactly this. So this would be mod c square by 2, because you have to take the gradient, and suppose we just take the gradient of these two and then just plug it back in. You would get, oh, now, okay, so one remark is that now this delta here is the perturbation, is the L infinity perturbation. Okay, now you extend this delta to all of Rn by 0 outside omega. Okay, so then my delta then would belong to L2 of R. And now I have, from this equation, we have that mod c square by 2 delta hat of c is equal to 0. So from here, this would imply that delta is equal to 0 almost everywhere. So therefore, the linearized Calderon problem is done. Now what we do is the next, which starts in an hour, I will focus on the nonlinear Calderon problem in 3 dimensions and higher. Okay, so I will stop here. I don't want to start a new topic. So any questions?
Venki, can I ask a quick question again?
Yes, please.
So, do you need any condition on this delta, like it's positive or negative, or any delta, only L infinity is good enough?
L infinity is good enough because this is just a perturbation.
Oh, right.
Right. Mm-hmm. Of course, you know, the thing is that, okay, you're only interested in delta small enough.
Right.
Right. Now, if you start with 1, right, then your delta is actually small enough in the L infinity sense. So your delta is actually going to be quite small, but okay, it's not going to be quite big, but you still need well posedness corresponding to 1 plus delta.
I see.
Right. So therefore your 1 plus delta should also be, okay, of course it is bounded above, but it is also bounded below. So you cannot have like delta to be -2, -3, things like that.
Right.
Okay. But delta is also a function.
Mm-hmm.
Right.
Okay. Yeah. Thanks.
Yeah. Okay, if no more questions, so I will stop here, and we will get back in exactly 1 hour. Okay, thank you.